Okay.
And we have the second talk of this session, Rainier Turok, joining us from Edinburgh, speaking about, sorry,
No, that's good. No, that's good.
a minimal standard model LCDM cosmology or clues to quantum gravity from reality. Stage is yours.
Okay, so thanks very much to Alessia and the other organizers. I think this is a very fun meeting. Combining people who probably are kind of similar in mentality, namely that we like taking on almost impossible problems. Quantum gravity is certainly one of those. And also who may be somewhat frustrated with let's say, the mainstream approaches, various of mainstream approaches. And that certainly describes me, and I think probably quite a few of the people here. And I think it's really nice what the organizers have done to bring together different strands in the hope that there'll be, cross-fertilization of ideas. So that's really important, and just want to thank them for doing that. So what I'm going to do is look at the answer, namely the universe, in the hope that we're going to get some clues about quantum gravity from observation. And I think if you look carefully at, well, what we've learned in the last 20 years, it does not fit very well with mainstream ideas. On the contrary, it's been surprising. And I think we need to learn from those surprises. And I think I'm going to give you an interpretation of those surprises. It's not necessarily the correct interpretation, but it's a very simple one. And I hope this will encourage other people to think of simpler ways, more predictive theories that might explain what we see. So I'm looking at the observations in order to get clues, of course, about quantum gravity. So this is mostly work with Latham Boyle, who's recently moved to Edinburgh with me and 3 students at Edinburgh. So lambda CDM, the current model of the universe, provides a remarkably good fit to all available data. And the data really has come in large quantities. And I think everybody has been surprised at how well this extremely simple model or fit really works. Okay. So the fit only involves 5 free parameters, which is remarkably few for something describing the largest structure we know of. 3 describe the energy, the cosmological constant, the dark matter to baryon ratio, and the baryon to photon ratio. And all of these are approximately constant, which is why we parameterize them. We use these as sort of fundamental numbers, which we need to come from some fundamental theory of physics. Only 2 numbers are required so far to describe the large-scale structure we see, apart from some anomalies, which you're working on, which are also interesting. But I'm going to take the point of view that perhaps this is all there is that we're going to get from cosmological data. And that seems like the way things are going. We need an amplitude for primordial perturbations. So if we express them as the variance in the Newtonian potential as an integral over Fourier mode K, co-moving Fourier mode, then integrating over equal log intervals of K, there's an amplitude. This is about 1 part in a billion. So we need to predict that number from first principles. And there's a small dependence on scale described by what's called a tilt. And this is just cosmological notation, ns minus 1. So the scalar index ns is approximately 1, telling you that the gravitational potential, dimensionless quantity, is approximately scale invariant on large scales. That's an amazing fact about the universe. And the slight tilt here is about minus 0.04. So the power spectrum gets slightly stronger as you go to longer wavelengths. And I'm going to interpret this later in the talk as a critical exponent, and we're actually going to calculate it in terms of standard model parameters. Very many parameters, which could have been there in the universe, given Einstein equations and description of geometry and the matter and the perturbations, many parameters have turned out to be zero so far. The tensor perturbations in particular, which I'll talk about, the smoking gun signal of inflation is not so far there. The curvature of space could have been allowed. It doesn't seem to be there. Non-Gaussianity, the perturbations seem consistent with the simplest probability distribution you could imagine, namely Gaussian random noise with this nearly scale-invariant spectrum. So 5 numbers we have to predict from fundamental physics. And what do our fundamental physics theories predict? 10 to the 500 compactifications with each one with vast numbers of free parameters. You know, we're really not doing very well. But I think the simplicity ought to encourage us to think there may be a simple description of the universe. Lambda CDM is extremely predictive. I was fortunate to get into cosmology before this quantity had been calculated. The polarization temperature cross-correlation in the CMB, polarization is very small. It's less than 10 microkelvin. So we calculated this correlation in 1994. There are no free parameters in that calculation at all, given the cosmological parameters which are fitted to the temperature power spectrum, and it fits beautifully. Okay, so this is part of what convinced me that something really simple is going on in the universe. The universe is extremely minimal. If you fit the 2 parameters I mentioned, the scalar amplitude and tilt to the temperature and the other cosmological parameters like Hubble constant, you predict this with no free parameters. There's no sign of inflationary tensors. As you all know, I'm sure, the bounds have been coming down for a while. I have several bets on this that I've betted on 0 because I don't particularly believe in inflation. And so far, I keep winning these bets. So I'm going to push my luck. And anyone like a bet on tensor being non-zero, please come to me. All monomial potentials for inflation are ruled out already. Here's 5/4 is not even shown on the diagram anymore, although this was the original guess for chaotic inflation. So this is all, these are ruled out. So you need a potential with a bend. It's the progress just a couple of years ago, this bound came down to less than 0.036. I would have won my bet with Stephen Hawking had he lived, because he bet on 0.05. And the limit is really going down fast. So it's predicted to go down to 0.003 in 3 years' time, and even further subsequently. It's a similar story in particle physics. On very small scales, LHC has seen nothing beyond the standard model. And that again was a big shock to most particle theorists. They were confidently predicting some sign of physics like supersymmetry or whatever. Didn't turn out to be there. No deviations from the standard model so far. So my basic question and motivation is, what is the simplicity, this unexpected simplicity of the universe on both very small and very large scales telling us about basic physics? Maybe our theories have become too complicated and artificial. Maybe we actually know the laws of physics already. Maybe it's just gravity and the standard model with some tiny, tweaks to make them, to reconcile them. Could a minimal extension of the standard model in GR describe the universe? And I think that's what we should be doing. What is the minimal extension of the laws we know which make them consistent of course, mathematically, logically consistent, and consistent with what we see. So I'm going to describe such a minimal extension. Inflation. There is a sort of minimal version of inflation, which is quite interesting, but illustrates inflation's deficiencies. And by the way, Renata referred to the early universe as being this little-like. That's assuming inflation. And I'm going to explain there is no evidence for that. In fact, there's evidence against it. And so you don't need. Correct, correct. So exactly. So the standard view is that inflation is necessary, and I'm going to explain why it may not be necessary. Nevertheless, there are sort of minimal versions of inflation, which I think are interesting because they are testable. One minimal version, perhaps the most minimal version, is Higgs inflation. So here you postulate the standard model Higgs based on a renormalizable quantum field theory. You add Einstein gravity to it, and then you do one extra tweak, which is you couple the standard model Higgs to the Ricci scalar with this coupling, which has to take a large value. And actually, the sign here is the opposite of the conformal coupling sign. So it's a little bit weird. But anyway, you can add this term. The weird thing is you insist on normalizability in this frame, okay, but then you couple it to gravity. So that's just a choice. It happens that with that choice, when you go back to Einstein frame, you get a minimally coupled scalar with an exponentially flat potential at large field values. So it's a kind of trick. It may feel like a bit of a sleight of hand. It is, but it does work and it does give you predictions. There is an amazing thing about the standard model, which is that the parameters, top mass, Higgs mass, lie very close to the boundary of vacuum metastability. And so if you look at the standard model Higgs potential, there's the usual vacuum, electroweak VEV. But then if the parameters go around the neighborhood of where they're measured, you find regions where the Higgs field would actually, or this field chi, would have another minimum. And so we would be metastable and we could tunnel through there. So that's very intriguing, not understood. Perhaps this points to some selection principle. The Achilles heel of this Higgs inflation is that, as I've mentioned, gravity is not renormalizable. So at best, this is an effective field theory. So you use renormalizability to justify this part of it, but then you sort of spoiled it by coupled it to gravity. So this is an effective field theory, and there are actually many free parameters in this setup. Nevertheless, what Shaposhnikov and people do is they include only a minimal set, what they call a minimal set of operators, assume 6d-fold to inflation. Of course, this picture does not resolve the problem of the initial conditions of inflation, the measure on inflation, et cetera, eternal inflation. Doesn't resolve any of that. But they assume that. And then with this value of psi, you predict spectral index and the tilt. This is great because this is going to be possible to measure. Targets for experiments, including these forthcoming ones. So here is Higgs inflation is this one. R-squared inflation, which was discussed yesterday, is over here. That's also great. That's, I would say, next to minimal. Compared to Higgs inflation, also has ambiguities and so on, but these are testable. And here is the projected increase in sensitivity of experiments going to CMB-S4, which may be able to get R less than 0.1%. So this is very exciting. We just have to wait, and my bet is they'll be ruled out. Okay, anyone who wants the bet, please come forward. Huh? You bet this will confirm? Any money. Any money. Okay. So, do we really need inflation? So here's our take on it. Our take on it is that you see, if you try to explain why is the air in this room almost homogeneous and isotropic, you don't need a mechanism. Statistical mechanics does that for you. The typical distribution of air molecules in a room is homogeneous and isotropic. But to understand that, you need a measure on the space of states. And in the context of inflation, there's never been a measure. It's always a guess, that we guess the inflaton started on its potential, and then we like this dynamical evolution. And so people like Penrose have criticized this very heavily as sort of putting the cart before the horse, making one assumption in order to explain something else, but the assumption you make is equally implausible. So our take on this is we need a measure. We need a measure on the space of universes, space of cosmologies. And we're going to take a guide from black hole physics, where there is a somewhat understood measure, the entropy of black holes, and we generalize that to cosmologies, and we calculate the entropy of cosmologies. And I'll show you how we do it. It's extremely simple. It's unambiguous. You may disagree with the principles, but it's crystal clear what the answer is. And it turns out it predicts homogeneous isotropic universes, which are spatially flat, as the most probable geometries. Yes?
So I thought if you rely on something
Yep.
to solve the horizon,
Yes. Yep.
which I think is a very good point.
Yep.
People can do this.
Yep.
But then that the fluctuations and the temperature predicted by statistical mechanics are in fact way, way too low.
Yes. Good. Good. Thank you. You're anticipating my talk. So first we're going to explain the homogeneity, and then I've got to explain the fluctuations. And the way I'll explain the fluctuations is by pointing out that QFT, the standard model in a curved spacetime, has a number of issues, namely vacuum energy is infinite, trace anomalies. We have a new mechanism to cancel those things, and that mechanism automatically gives fluctuations on large scales, and they happen to match what we see, both the amplitude and the tilt, with some assumptions, okay? So, so good point. That's what I think convinced people about inflation, is it got the fluctuations roughly right with some parameters. But, not so fast. It's a phenomenological model which fits what we see, but, you're fitting two numbers. You don't need to be convinced by a phenomenological model with many parameters which fits two numbers. Okay, so let me keep going. CPT is the most basic symmetry in physics, okay? I think nobody would disagree with that. It's based on Lorentz invariance and analyticity. We made the radically minimal hypothesis that the universe is CPT symmetric, okay? Despite appearances. Okay, so we know there's more matter than antimatter in the universe. We know there's an apparent arrow of time. They seem to violate CPT, but what we noticed is that if you take the standard hot Big Bang cosmology without inflation, okay, radiation dominated all the way back to the singularity, there's the surprising fact that the scale factor of the universe in conformal time is linear in time. Okay, it's the simplest possible zero. So the universe apparently evolved out of a simple zero of the scale factor towards a simple pole. Okay, for anyone who likes complex analysis, that's pretty amazing, that the analytic structure of the actual cosmos is so simple. Now, what we do is this, obviously, since it's analytic, you can extend through t equals 0, and you find an identical space-time on the other side. Yeah, question? Sure.
So in GR, it is known that in the absolute zero of time, there is Meissner initial chaos, basically.
Good point. I will explain the chaos. There is no chaos in this picture. The chaos is removed by CPT. Okay, I'll explain exactly how. So this resolves why there's no chaos. It also tells you the peak. It tells you the phase of these curves, right? This is a particular phase of oscillations. There are two modes for the radiation in the universe. There's what's called a growing mode and a decaying mode. And if you add them in arbitrary combination, you can move this phase around. This phase corresponds to the growing mode. That growing mode is the CPT symmetric mode. Okay, so this is what got us excited about this idea in the first place, is if the universe respects CPT, we get that oscillation mode correct. We don't have any vorticity. Vorticity violates CPT. It's also a puzzle. Why did the prime model universe not have any vorticity? Go ahead.
Using CPT symmetry or CPT symmetric in a different way to the way I usually understand it, because to me CPT, to say that physics, say quantum field theory is CPT symmetric, means that a particular solution of the theory, if you do CPT transformation on it, then that is also a solution, but not the same solution. I mean, it doesn't, when you do a
That's right.
minus T transformation on,
Mm-hmm.
you know, on some, in classical mechanics, on some history, then you don't get the same history back, but you get something which is also a solution of the equation of motion.
Right.
So this picture and the way you're speaking indicates to me that you're requiring something stronger than that, which is that actually the actual solution,
Correct,
if you do this transformation,
is invariant.
is the same.
Yes, there's an isometry. CPT is an isometry. Yeah, that's the assumption.
I think you are using it differently to the way I usually.
No, I mean, that's the symmetry of the laws of physics, let's say in flat space-time. So you take an isometry of flat space-time, and when you write down the laws, you insist they respect that isometry. We're noticing that there is a corresponding isometry to cosmological space-time, or there can be, and then I can study quantum fields, etc., within this space-time, and again make the assumption that the vacuum state is CPT symmetric. That's what we're going to assume, and so there is an isometry of the space-time one can use to. There's an isometry of the laws, and you can choose to impose that isometry on the states, and that's what we do. Yeah.
Maybe following that up, do you have any deeper reason for assuming that CPT is used in this fashion constrains the solution rather than relates solutions, as Faye was just mentioning?
Yes, I'll explain in a moment. Sorry. You're asking how does it constrain the solution?
Well, I'm asking if there's a deeper sort of motivation for choosing only the CPT.
Well, I think the deep motivation is that the laws of physics are apparently CPT symmetric.
Good.
Okay.
But that doesn't mean we always have CPT.
Correct. Correct. So then the assumption is that that symmetry is not broken by the physical state of the universe. That's the assumption. If you have a symmetry either. Initial condition, yeah, it's not broken by the physical state of the universe. That's the assumption. Okay, it's certainly the simplest assumption.
So I was looking.
No. Okay, so this picture requires, or the reason for the analyticity of the scale factor is that the stress tensor for radiation is traceless, T mu mu. So from the Einstein equations, the Ricci scalar is 0. Just look at the Ricci scalar for a cosmology, and you'll find that if the Ricci scalar is 0, it means the scale factor vanishes linearly in time as t goes to 0. The spatial curvature becomes unimportant, and basically the Ricci scalar becomes proportional to a double dot. And if you since it has to be 0, A has to go linearly with T. We think of this, of imposing the CPT by the method of images. Okay, we don't really understand what's happening near the singularity. So we imagine an initial state for the universe, if you like, which is precisely the CPT conjugate of the final state. And then we look for, so if you think of doing a path integral, you're doing a path integral over 4 geometries between some initial and some final state, which happen to be identical. And then you find saddle points. And so this statement of analyticity is a statement that these are genuine saddle points of a path integral. Now, this picture generalizes to inhomogeneous, radiation-dominated cosmology. Half of the solutions, so if I do this, if I say I've got some 3 geometry at late times, I take exactly the same 3 geometry at some pre-Big Bang time, using this method of images, and I ask, are there solutions of the Einstein equations which join the 2, right? And the answer is there are. Half of the solutions of the Einstein fluid equations are time reversal symmetric, and these correspond to a completely regular conformal geometry. Okay, so in other words, that result of the homogeneous cosmology generalizes to inhomogeneous cosmology. The conformal 3 geometry provides a complete Cauchy data for the evolution of this universe on both sides of the singularity. So now it's actually very cute, because as I mentioned, you're going from a 0 to a pole. That suggests you can solve the equations as a power series around either of these. Here it's just a power series in T, involving only even powers of T, because it's time reversal symmetric. Here it's a power series in 1 over T, because it's heading towards a pole, and you can do a power series, and it turns out you can solve the equations, homogeneous and inhomogeneous, by matching 2 asymptotic expansions. And so while the exact solution is a Jacobi elliptic function, in fact, you can get that just by matching these 2 asymptotic expansions. And this even works for the inhomogeneous cosmology. Okay, so the full nonlinear Einstein fluid equations can be solved in a covariant gradient expansion at spatial gradient. So this only works for long wavelength modes, but this can be done. It's a kind of double holography, and these are an analog of the Pfefferman-Graham expansion. Okay, let's talk about thermodynamics. Black hole thermodynamics. So it's an ancient subject, still not completely resolved, though a lot of evidence has been accrued. And the basic idea is very simple. We make time imaginary. So T is minus I beta. Beta is 1 over the temperature. And we identify initial and final states and trace over them. And so the statement is that an amplitude in quantum theory will give you a partition function if you go to imaginary time and impose periodicity. So Hawking and others noticed that black hole spacetimes are periodic in imaginary time, and therefore they are consistent with this picture. You view them as saddle points of this path integral, and the Hawking temperature is nothing but the imaginary time period, and the gravitational entropy of a black hole can also be calculated. It's just the action, the Einstein-Hilbert action, calculated over 1 imaginary period. And again, that's a formal argument which follows from these ideas. So the partition function, if you do calculation with matter radiation present and coupled to gravity, is equal to the ordinary, the exponential of the ordinary entropy plus the gravitational entropy. So here are the laws we have in the path integral for gravity and the standard model. We're going to impose periodicity in imaginary time and then calculate the partition function. So how are we going to do that? We're going to approximate all this stuff as a fluid so in the first instance, we'll take this fluid to just be radiation. There's an action for radiation. You can So put in the appropriate action for the radiation, find the saddle points of this path integral, and calculate the action. So let's look at a realistic cosmology. Here's the line element, where I'm allowing spatial curvature. This is the scale factor in conformal units. And then this is the Friedmann equation or constraint equation, that A dot squared is the radiation matter, if we have matter present, space curvature, and lambda. And then amazingly, people didn't notice until recently that this equation has solutions which are all periodic in imaginary time, just like the black holes. Okay, so cosmology shares this property. Also, like black holes, it's two-sided. Right? I showed you this double-sided universe. This is the same as black holes. We know that Schwarzschild spacetime has two asymptotic regions, and that's a general feature of solutions of the vacuum Einstein equation. So it happens to be the same feature in cosmology. So in making sense of cosmology, we're actually going to come up with a suggestion for black holes as well, that black holes should be CPT symmetric as well. And this leads to another perspective on black holes. So it's two-sided and periodic in imaginary time. So you look at A of t in the complex t plane. A of t runs from the Big Bang to the future de Sitter singularity. That's the pole. And then we just go into the complex plane, and it does very similar things. And in fact, the complex plane is tiled periodically with poles and zeros. Fundamental domain is a rectangle for this mini superspace, if you like, cosmology. And so both the real part of A and the imaginary part of A are doubly periodic functions in the complex plane. The imaginary time period determines the Hawking temperature, and the action calculated over one period is the gravitational entropy. So, you know, they are what they are. They're completely unique. We have, in making this picture, we're treating singularities as poles, and treating the zero in particular at the Big Bang as regular. Okay, so there's a Euclidean instanton for every value of the radiation, matter, curvature, and lambda, and we calculated SG. So we use these CPT symmetric boundary conditions. We also study inhomogeneities. I won't show you that, it's more messy, but you just take the Euclidean action for gravitational waves, for density perturbations in the radiation, and you find that the Euclidean action for those is positive, and therefore they decrease the gravitational entropy. Yes. 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 You basically go through the Einstein static universe. So there's a sort of phase transition. You have de Sitter-like, which is S4. You go to the Einstein static universe, which is S3 times the line. And yeah, so the topology of these instantons is different than the de Sitter. Yeah, thanks. Okay, so being naive, the entropy provides a measure on cosmology. It tells you how many states there are. For any particular universe, I can tell you how many states there are in this approximation. And it just happens this is greatest for homogeneous, isotropic, and spatially flat universes. Basically, this gravitational entropy goes like kappa, the curvature parameter, kappa to the minus 3/2. And so it's biggest when kappa goes to 0. It also goes like 1/λ, right? And this is actually a well-known fact. The entropy of de Sitter spacetime goes like 1/λ, and this was argued a long time ago by Baum, Hawking, and others, that this is the reason why lambda is so small. They thought it was 0. Okay, it's not 0. This is a thermodynamic explanation of the large-scale geometry of the universe. Okay, there's no need for inflation. But, comes with a big but. This gravitational entropy is a global quantity, global property of the space-time. It is independent of time, the gravitational entropy. You can't think about it of the entropy of the initial conditions or something like that. That doesn't make sense. It's the entropy of the space-time. So it requires a global view. It's not an equilibrium configuration. Obviously, the universe is not in equilibrium. And in fact, in general, gravity does not allow thermal equilibrium. So we have to get used to counting states for non-equilibrium systems. This is a nice picture in Quantum magazine that if you picked universes at random, according to how many there were, you would pick one that looked like ours. We can include matter. So here the entropy and the radiation. This is the normal entropy, T cubed times the volume, divided by the de Sitter entropy, S lambda, to an appropriate power. Turns out that everything is sort of determined by these parameters. There's a simple scaling. And if you vary the radiation entropy, the total mass in the universe, these are the globally conserved numbers specifying a spacetime. You can now plot the total gravitational entropy in terms of S lambda. And what you notice is that going up in gravitational entropy, this is gravitational entropy of 1,000 times de Sitter, the universe becomes spatially flat. This is the omega in curvature. This is the dimensionless contribution of the curvature term to the Friedmann equation. So the higher the entropy, the flatter the universe. This actually also suggests an explanation. There's a puzzle in cosmology. Why is the matter-radiation transition so close, apparently, to the lambda matter transition? Right? These three ingredients in the universe. And it happens to be that matter took over from radiation and then lambda took over from matter quite nearby. This suggests an explanation of that in terms of equipartition, that all of them contribute roughly equally to the total gravitational entropy. But I emphasize we still need to understand how to impose the constraints. When you do thermodynamics, it's meaningless to ask what's a typical configuration of gas in a box. If I don't tell you any other information, you can't tell me. I need to tell you the conserved quantities. I need to tell you the number of atoms, or molecules, and I need to tell you the total energy. So you need to put in some numbers in order to get out other numbers. My current guess is the numbers we have to put in for the universe correspond to a large universe. We will have to put that number in. And if we put that number in, we will then predict the matter density, the radiation density, the lambda density from such a constraint. But we still don't understand how to do that. Now I want to talk about quantum fields in curved spacetime. So let's get to the fluctuations. That's my goal, because inflation's huge success was explaining these approximately scale-invariant fluctuations as a property of scalar fields in de Sitter spacetime. Okay, I'm going to do it in a completely different way, in a way which has its own problems, but which has much more motivation and which apparently gives a parameter-free prediction which agrees with the observations. And no tensor modes. That's why I'm so confident. Okay, that you're all going to lose. Okay, we'll see. Quantum fields in curved spacetime. Well, the first thing that hits you in the face if you tried to do quantum field in curved spacetime is the vacuum, energy, and pressure are divergent. And I was very interested in Roberto's talk, where this apparently goes away as the universe gets bigger, the divergence goes away. I think I understand why. And it's because there's no dynamics in your calculation. So basically you are using Einstein's, at least Reuter is using an Einstein static universe where the radiation is the radiation is the vacuum fluctuation. So these are divergent, at least naively, okay? Though I find Roberto's example very interesting. These can be renormalized away, but it's very concerning that the vacuum's full of stuff which apparently gravitates. Likewise, these divergences spoil the local scale symmetry of Maxwell and massless Dirac fields, which is surely a very fundamental symmetry of the basic ingredients we know exist. So these are trace anomalies. So if I put Maxwell fields or massless Dirac fields like occur in the standard model, if I put them into a curved spacetime and compute the stress energy, the trace of the stress energy, I find it's not zero. And these are the, and these cannot be renormalized away. So this is a big problem for us, because if we really want to say the Big Bang singularity is resolved and is a simple pole, we need some way to cancel this trace anomaly. There are lots of other reasons to cancel a trace anomaly, by the way. I may have time to show you some of them. Standard model fields all contribute, so spin, 0, half, 1 fields all contribute positively to these anomaly coefficients, so you can never get a cancellation. We have a tiny generalization which allows us to cancel all the trace anomalies and the vacuum energy. The minimal cancellation mechanism we claim are dimension 0 scalars. Okay, so there's actually a very old theory, originally proposed by Heisenberg for nuclear physics reasons, that you have a scalar field with 4 derivatives in the action. So its dimension is 0, and it's there is a locally scale-invariant version of this action. You add in the appropriate Ricci terms, and this is Weil invariant action, discovered by Panietz and others. Canonical quantization leads to negative norm states, but as in a gauge theory, these can be removed, at least in the free theory, using an infinite dimensional symmetry. This was discussed by Bogolubov in the 80s. If you do that, the only remaining physical state is the vacuum. Turns out this symmetry just removes everything, all excited states. There's only a vacuum, and this vacuum has scale-invariant fluctuations. Why? Because this is dimension 0, so it has to be d3k over k cubed. That looks like the 5 fluctuations in cosmology. So actually, this was our reason for looking at dimension 0 fields. These are fields which automatically have scale-invariant fluctuations in the vacuum. So a priori, they're what you need to explain what we see. Long wavelength, infrared fluctuations. And then we found the following. The dimension 0 scalars can cancel the anomalies in coupling the standard model to gravity. Here's the vacuum energy. It's just free field theory. H bar omega times the number of dimension 1 scalars, -2 for a chiral fermion, +2 for a gauge boson, the 2 helicity states. Dimension 0 scalars, roughly because they have double the number of derivatives, have a factor of 2 as well with the plus sign because they're bosons. So these are very well defined, contributions to each mode in the vacuum. Conformal anomaly goes like some funny numbers. The other term, these are the A and C coefficients, also well known. You notice these dimension 0 scalars have minus signs. So now you can cancel. If you impose the 3 equations, these are 3 equations for integers, for 4 integers. The 3 equations together imply that there is no dimension 1 scalar. Yeah, this is very sad because I hold the Higgs chair at Edinburgh. Okay, this is telling you that the Higgs cannot be a fundamental degree of freedom. NS1 is 0. That's actually not a problem, I don't think. I think it's an opportunity because the Higgs scalar, we have the terrible hierarchy problem. And if the Higgs scalar is composite, that may indeed help with solving the hierarchy problem. So, optimist that I am, I'm not put off by this prediction. Now look at the other equations. Any 2 of these 3 equations give that the number of fermions is 4 times the number of gauge bosons. That happens to be true in the standard model, that if we have if we have right-handed neutrinos. Okay, so if we have 16 fermions per generation, 3 generations, then the number of fermions is 48. The number of dimension 0 scalars is 3 times the number of gauge bosons. The number of gauge bosons, I should have said, is 12 in the standard model. There's SU3, SU2, and U1, so 12 gauge bosons. So number of fermions is 48, and the number of dimension 0 scalars is 36. Okay, so for this magical 36, we cancel all these numbers. And this is really surprising that this cancellation is possible. So we predict 3 fermion generations, each with the right-handed neutrino, but it's extremely naive calculation. Yeah.
So you have 3 equations for unknowns.
Right.
What's the...
Well, they have to be integers. That's the constraint. Okay, so with 3 equations for 4 unknowns, you generally will have 1 free parameter. Okay, so but nevertheless, yeah, I mean, what I say, if you set all 3 to be 0, it actually forces this number to be 0. And yeah, so what I say here is a consequence of those equations. But it's not clear, it's not obvious at all that there would be a solution. Let's see, if we set ns1 to 0, 3 equations, 3 unknowns, not obvious that there are integer solutions, and it happens that there are. Okay, so yeah, I mean, basically 3 equations being 0, right? You're only going to ever determine the answer up to an overall number. But what isn't obvious is that the relative numbers are integers. Gravitational, I won't dwell on this, but just to mention that the standard model coupled to gravity, and this is something John Donahue has worked on, and Tom Boulis in the 70s, I think this has long been known, but just take gravity and I put in standard model loops, and I sum them all up, I get this propagator, right, which looks like this, and this is pathological. So coupling the standard model, in a sense I'll make clear, the standard model loops coupled to gravity lead to pathology of a certain kind, okay? And the pathology is, first of all, it's inconsistent with Callan-Lehman. Callan-Lehman tells you that any propagator can only be a weighted sum of normal scalar propagators that can only fall as fast as k squared. This one falls like k to the 4th, so at large k. So, and Callan-Lehman is a result of Poincare invariance and positivity, so this is a little bit worrying. Furthermore, it has complex poles on the physical sheet, which would also require some arguing about, and John has tried to make sense of these. But so similarly, these dimension 0 scalar loops alone, coupled to gravity, also have similar problems. They induce a tachyon in the graviton. The graviton now has a tachyon. These are pathologies, but if you put them in combination, in just the right combination, all of these things cancel. So basically what happens is all of these diagrams are 0 if you include these dimension 0 fields. So this really matters for the properties of gravity. Perturbations. Okay, so can I have 10 minutes? Okay, thank you. Primordial perturbations from dimension 0 fields. So we use the dimension 0 fields to cancel the vacuum energy and the trace anomalies at free field order. But those are not, the standard model includes violations of scale invariance when you include interactions. The coupling constants run with scale. Okay, so there are running couplings in the standard model. So for example, if I calculate this trace of standard model matter, stress tensor 3p minus rho, it's not 0. It should be 0 for pure radiation, but it's not 0 at finite temperature. This trace goes like alpha squared. And this is just the part coming from the gauge bosons. Fermions will give a similar kind of contribution. And these coefficients are related to the beta functions. The trace of the stress tensor is related to beta functions. It is directly related, and these coefficients which come in are as follows. So SU2 and SU3 give negative coefficients. U1 gives a positive coefficient. So this is completely calculable, and it's telling you that in the standard model at high temperature, 3p minus rho is not zero. So we have to cancel it. To cancel it, we've used a trick, which is similar to a trick used in string theory. In string theory, if you put a string in a curved background, you find the stress tensor, the 2D, the worldsheet stress tensor, is not traceless. And so you couple the dilaton to the Ricci scale on the worldsheet via a term which classically is not Weil invariant, and you use that coefficient to cancel the quantum anomaly in the trace of the stress tensor. So we've just done the same in 4D, okay? Namely, we add a term to the action, which would be a total divergence if there were no dimension zero field here. So that would do nothing. But just as in the string theory analog, this would be R, the 2D Ricci scalar, and which is a divergence in 2D. So we do the 4D analog, couple to phi, and we also couple the trace of the standard model stress tensor, this T beta, to phi. What happens is that when you calculate the trace of the stress tensor in this theory, the variation with respect to the metric here, or the conformal factor of the metric, gives you box squared phi. The variation, so basically you get the anomaly is box squared phi. This term is Weil invariant, but this is not Weil invariant. So I get a classical contribution, which is box squared phi. Then I vary with respect to phi, and I see that from the phi kinetic term, box squared phi is t. So basically I get a contribution to the trace anomaly of proportional to the standard model trace anomaly, and I can use that to cancel it. Okay, so we just use this cancellation mechanism to cancel the contribution of standard model running couplings to the trace of the stress tensor. But now this last term, the coupling to the stress energy trace with phi, of course, will now enter the Friedmann equation. So it means that phi enters the Friedmann equation linearly. Phi has scale-invariant perturbations, and so the spatial curvature of the universe will pick up scale-invariant perturbations. From the constraint equation, actually, the best way of thinking about this is on the initial hypersurface, you've got to impose the Einstein constraint equation. That constraint equation involves phi, and it involves the 3 curvature. And the 3 curvature automatically picks up scale-invariant perturbations. So there's some technical assumptions, which I can discuss in more detail. We found that imposing this condition implies the following power spectrum. Power spectrum of the co-moving curvature. This is a quantity cosmologists like to use. It's the spatial curvature Ricci scalar of the constant density slices in a cosmology. And we can calculate this from first principles, more or less, with some assumptions about the running of the alphas with scale. And here's the answer. Okay, so here's the amplitude in terms of standard model couplings. Number of degrees of freedom comes in. This is including right-handed neutrinos. The tilt is negative because of asymptotic freedom. Asymptotic freedom tells you that alpha, the strong coupling constant, gets weaker at large momenta, so stronger at large scales. And this tilt is exactly coming from there. And it turns out that for the observed values of, using the measured values of alpha at LHC, extrapolating to the Planck scale, okay, so long extrapolation, the tilt is just -7 alpha 3 over pi. Alpha 3 is about 1/30th. That number gives you 0.04, which gives you which gives you NS of 0.958. We also predict the amplitude, and amazingly, this is only a factor of 2 away from what we see. Okay, so this theory, although it has a bunch of assumptions, is already doing much better than any inflation model. Potentially a much more predictive theory than lambda CDM because it's really connecting the smaller scales in physics. An extrapolation of LHC up to the Planck scale, it's connecting that to the large scale structure in the universe. I was going to talk about dark matter. I won't. That's another story. The dark matter is a right-handed neutrino. What I want to emphasize, this is a thermodynamic explanation for the large-scale geometry, a new way to cancel standard model vacuum energy and trace anomalies, predicts 3 generations. It gives you the simplest yet explanation for the dark matter in the universe. It's a right-handed neutrino, and the baryon asymmetry is explained with right-handed neutrinos. That's not a problem. So this is clearly only the beginning, and I hope what it will do, it's not necessarily correct, it is testable, but I hope what it will do is open people's minds to the possibility that inflation may not be the last word. Thank you.
Thank you very much for this inspiring talk. We have like 2 or 3 minutes for some questions, so yeah.
Yep. Yep.
I like the idea.
Okay.
It's also written in old Sakharov paper.
Absolutely. It's not just 2 lines, it's a whole paper on CPT's symmetric universe. Yeah, no, I should have given references. Sakharov had this idea. There's prior work to Schrödinger we were discussing this morning that on de Sitter space-time. So yeah, these ideas do go back quite a way. Sakharov has quite a good record of anticipating important ideas. Right. Exactly. I didn't talk about it. Yeah, so the beautiful fact is that the standard model on its own violates baryon number at high temperature through anomalies, through chiral anomalies. And so if you have a right-handed fermion, we have to have one to have 48 fermions. If you have a right-handed neutrino, that violates lepton number. And then as the universe cools, and these right-handed neutrinos decay, they violate the decays, the non-equilibrium decays actually violate lepton number. That gets converted into baryon number. And so all of that is sort of contained within this leptogenesis scenario. So in other words, what we're claiming is, give me the standard model with right-handed neutrinos, which you can argue are very strongly motivated by neutrino masses, by the observed neutrino masses. And give me that, impose an extra symmetry to make one of the right-handed neutrinos stable, then it's the dark matter. Okay, this is very easy to arrange. You have enough parameters remaining to explain the baryon asymmetry. So yeah, in principle, all of the numbers which I gave at the beginning are all explained.
Maybe one very short question. Thank you. Very briefly.
Yeah, that's true. You mentioned cancellation.
Yeah.
Scalar. Anomaly.
Yes.
Curious contributions to the propagator.
Oh, yes, that's right. That's right. No, they're not. No. So, yeah, that's a funny thing about these trace anomaly coefficients. Let's go back to those. Whoops. These trace anomaly coefficients, these numbers are related to the strength of correlators in the CFT in flat spacetime. So there's this relation, I don't fully understand it, but there are 2 ways of calculating these numbers A and C. Either you do free quantum fields in a curved spacetime, Or you just do free quantum fields in Minkowski space, but calculate the correlation functions. And because the stress energy is quadratic in the fields, there are non-trivial correlations. So there's a 1-point function, 2-point function, 3-point function. And these numbers are related to those. So it turns out this, here I actually have the 2-point function of the stress tensor of this field. That's exactly what I have here. So if you cancel the 2-point function, it turns out that the coefficient of the 2-point function is exactly the Weyl squared trace anomaly. And if I did the 3-point function, it would be the other coefficient. Okay. So what we are doing in flat space-time is canceling the 1-point function, the 2-point function, and the 3-point function of the stress tensor in the vacuum. It's another way of saying it. It's strange you can do that, but
Okay, let's continue again. And considering the time, we will reconvene at 11:45.